So this session is an introduction to roots and radicals. So this is associated with section 8.1 in the textbook. I do have videos on already in the class that covers basically everything that you need to know, but this goes into a little more depth. Do you have to take college algebra? Do you know if you're going on to that?
I'm actually interested in taking as much math as possible. I just don't really know what
Okay.
I'm doing yet, honestly.
Then taking as much math as possible until you figure it out is a good plan.
Right.
Well, college algebra will use the material from this section, so it's good that you're watching this then.
All right. I'll keep the notes then.
Yes, definitely keep the notes. So I'm going to just start with square roots because that's what everybody is familiar with. People pretty much know what a square root is. And it is actually defined in terms of the exponent. So we say that b is a square root of a. So like 2 is a square root of 4 if that b, 2 squared, is equal to 4. So it's defined kind of backwards from what you might think with the square root. But we define it this way because the square root is basically undoing an exponent. And so all of the roots kind of work in terms of undoing exponents, and we look at them in terms of exponents. So that's why it's defined this way. So the actual symbol that we use for square roots is called a radical. It's called the radical sign. And so you'll hear that a lot if people talk about simplifying radicals. That's what they mean. That it's used generally for if you have something that's not a square root, but we have other types of roots like cubed roots. So radical is the more general term. So using this symbol, and we saw this in section 1.3, is if you have 3 squared is equal 9. So if you're taking the square root of 9, then your answer is 3. But also, if negative 3 squared, when it's in parentheses like that, also gives you a positive 9 because a negative times a negative is a positive. So the square root of 9 can also give you a negative 3. So the square roots can basically give you two answers. You can get a positive answer and a negative answer because whether it's positive or negative, when squared, you always get a positive out. So most of the time we assume the positive solution, and that's called the principal square root because that's the one that we use most often. If we're not doing any solving and we're just putting things on a calculator, you're just calculating it out, we always use the positive square root. So that's why your calculator will always give you the positive version. However, when we start solving and you're looking for an unknown, like you're solving for x, then you have both possibilities, the positive and the negative, because you don't know which one you want, and both of them technically work in the equation. So when you get to solving, you do have a positive and a negative, and we represent that by putting a symbol in front of the square root called a plus or minus symbol. So it's just a plus and a minus on top of each other. So when you go on to solve with the quadratic formula, that's why that plus or minus is there, is because you could have the positive version or the negative version. So it really is up to you on knowing when you need to use both. So the key is if you're solving and you're taking a square root, you need both. If you're not solving, you're not looking for a variable, then you don't. So that's the key. So that's the difference there. So we're going to go through all of these values of square roots, and you can do these on your calculator. You can do them by hand. I actually recommend that you memorize the common square root symbols or the square root values because they pop up often enough that it's good to recognize that I can take the square root of this number, because it also helps with factoring and all that. So I'm going to start with, we've got the square root of 25. So I'm going to show way more work than I usually do. But 25 is 5 squared. So we can really say, okay, this is the square root of 5 squared. So I mentioned that square roots are undoing an exponent, it's undoing the exponent of 2. So it basically cancels that out and you get 5. So a square root is asking what squared gives me 25. And so that's 5 squared. So you can do that on your calculator, you'll get 5. Now the next one, if the negative is in front, that's totally fine. What happens is we end up with a negative, and then you have your square root. So if you were to take the square root of 16, 4 squared gives you 16, so that would be a 4 as a result of taking the square root. So when you take the square root, when you actually do that operation, the square root symbol disappears. Sometimes I see people leave it there, but it disappears once you've taken the square root. So we end up with a negative 4 here because the negative is outside of the square root symbol. Now the square root of 0, this is 0 squared equals 0. Basically 0 to any power equals 0. So the square root of 0 is always equal to 0. Next we have the square root of negative 64. So if you were to do that on your calculator, some calculators give different types of errors. Mine says domain error. And this is because based off of our definition, we're saying what squared gives you negative 64. Well, anything you square always gives you a positive. It's not possible to get a negative. So that means that there's no solution to this, no real number basically. So you cannot take square roots of negative numbers. If you try, your calculator will give you an error. Now, when you go to college algebra, you'll learn that there's a special unit called an imaginary unit that allows you to get around this, but calculators aren't programmed to do that. So that's where you have to then know that even though your calculator tells you that it's an error, you actually can do this. But that's in college algebra, that's in higher levels of math, so you don't have to worry about that here. But you do want to know that if you're taking the square root of a negative, until you talk about complex numbers and imaginary numbers, we're going to say there's no real solution. Or you can write it's not a real number. Both of those are correct. That you just can't do it. Next one, we have a square root with decimals. So it looks like, oh man, I don't know how to do a square root when there's like decimals involved. But if you know that the square root of 81 is 9, because 9 squared gives you 81, you can see that this actually isn't bad at all. So when you put that on your calculator, we get 0.009. So the zeros stayed exactly where they were. We just took, oops, once I take the square root, I don't need the square root symbol. The zeros stay where they are. You basically are just taking the square root of the actual number part, the 81, and that gives you 9. Now with fractions, again, you might think, oh my goodness, this is, I don't know how to do this with fractions, but it's actually, again, not bad because we are allowed to actually split square roots up. If you have a fraction and you have things divided, you can actually turn it into 2 separate square roots. And so then you're just dealing with whole numbers. You're not actually dealing with fractions. And the square root of 1 is always 1. And the square root of 121 is equal to 11. So this comes out to 1 over 11. And you can even verify that on your calculator. If you do it on your calculator and you're not using like fractions, it will give you a decimal version. But if you convert that decimal to a fraction, you'll get 1 over 11. So you can double check that. It will come out to the same answer. Are there any questions so far?
No questions here.
Okay. So simplifying these square roots, because this is something that you have to do when we get to quadratic equations and we have the quadratic formula. So all of the ones that I did, except for the one with the negative inside the square root, they all came out to whole numbers or the fraction, but still whole numbers were involved in that. It wasn't really nasty. Not every square root comes out that nice, and in fact, most of them don't. And so if you pick like random numbers like the square root of 35, you're going to get some decimal. Square root of 29 is going to give you a decimal. Most square roots actually give you decimal numbers, and they're decimals that go on forever. So they're kind of like pi in that they go on forever, and there's no way to turn it into a fraction or anything like that. So if you get a square root and it comes out to a decimal, instead of turning it into decimals, we usually leave it in square root form because it's just nicer to look at. I know you might think the square root symbol is not nice to look at, but it's better than looking at a whole bunch of decimals. So we usually just leave it as a square root if it doesn't come out to a whole number. The only ones that we try to simplify are those whole numbers. And then if you're using a word problem, you have something in the real world, we usually do use decimals because decimals make more sense in the real world, but we round those to 1 or 2 decimal places. So that's just depending on the application. Usually just 1 or 2 decimal places is fine. And if we want to talk about, let's say I wanted to round this to 2 decimal places, this 29, I can put a line there. I want 2 decimal places, and then I look at what's after my line. If the number after that is 5 or higher, you round up. So this would round to 5.39 if we were to round that to 2 decimal places. So square roots are something that you're probably somewhat familiar with. You've had to work with them before. What's going to be new are these other types of roots, and we call them nth roots, where n just stands to some exponent. So we don't always like want to cancel out exponents of 2. We could have exponents of 3, exponents of 4, exponents of whatever number you want. And so those are just called nth roots. So if the exponent is 3, instead of calling it a third root, we call it a cubed root because the cube has 3 sides. But we've got the 4th root, the 5th root, the 6th root. The rest of them follow that pattern of the th kind of thing. So basically the definition is the same. It's just a different exponent instead of 2. And we do a small change on the symbol because we're adding a number kind of above the little, I forget what the name of that little symbol is, that V thing. But we're adding a number above that. Might be a 2, could be a 3. So normally we write a square root by this. And this is the same thing as if I wrote that symbol with the 2 right above there. It's just most of the time we don't write the 2 because we just assume it's a square root. That's the most common root. But you could have things that are cubed roots, and so there's a 3 right above it. And you want to be very careful because this does not, if I had a number in front, like let's say I had 2, and then I have the cubed root 3 of like, I don't know, like x or something like that. This is not the same as 2 to the 3rd and then the square root of x. So you have to watch where that 3 is placed. It's placed kind of above the V part of your symbol. That's what makes it go with the symbol. If it's to the left of the V part, then it goes with the number. So you want to be very clear. And sometimes people will draw like a little dot in between to make it clear that that's not part of the whatever number's in front. So just be careful when you're looking at homework problems that you're interpreting these correctly. And then also when you're writing the work yourself, that you're not accidentally getting yourself confused and thinking it's an exponent. What's not an exponent, it's actually part of the symbol. So just some terminology here. The N is called the index, and then the A is called the radicand. You don't really see the terminology for radican too often, but index does pop up. And actually, I recently learned that the order of operations in the UK they use instead of PEMDAS, they use BIDMAS. So RE stands for exponent, they use I for index. So that was something that I just recently learned, and then they use B for brackets, and then they put the multiplication and division in the other direction for their letters, but of course we always go left to right, so it doesn't matter. That was something that I learned recently, is that they don't use the same acronym that we do, and the I meant index, which was new to me. And then I wrote the notes for this, and I'm like, that makes sense. So these nth roots, let's take a little bit closer. Like I said, we've got the square root symbol, and then if you have a 2 up there, they both mean that you're taking the square root. If there's a 3, that's the cube root. That's the other common one that you'll see. You'll see cube roots. And those are reversing exponents of 3. So whatever the number is that's above the V on the symbol, that tells you what exponent you're undoing. So the cubed root of 8 is equal to 2, because 2 to the 3rd power gives you 8. Now this is interesting because the cubed root of negative 8 gives you negative 2, because when you have odd powers, you can get negative out. So unlike the square root where we couldn't have a negative under the symbol, you can for cubed roots, or odd roots basically, because you can get negative answers out when you take the exponent there. And then some other symbols are the 4th root, the 5th root. The only difference is that there's a different number up there, and that just tells you what exponent are you paying attention to that you're trying to reverse. Are there any questions so far?
So far, so good.
Excellent. So this is a slide that I recommend printing out or taking a screenshot of. These are very common squares. So the ones that come out to whole number we call perfect. So you've got perfect squares, perfect cubes, perfect 4th and 5th powers don't have special names. But these are things that you can take the square root of, the perfect squares. Perfect cubes you can take the cubed root of, and so on. So these are the ones that I recommend that you memorize, because it's quicker than doing it on your calculator if you just instantly know, oh, like 64 is 8 squared. So that way you know the square root of 64 will give you 8. I actually have memorized up to 15 squared, but that's a little bit overkill for you guys. But at least memorizing the squares from 1 to 12 will make your life a whole lot easier. And then out of the perfect cubes, you certainly don't need to know all of them, but at least the first 5. Especially like 2 cubed, that usually shows up a lot, and 3 cubed usually shows up a lot. The 4 cubed and 5th cubed, those are less, those don't show up as often, but often enough that I have eventually memorized those. The 4th powers, I would memorize even fewer of those. 2 to the 4th is equal to 16. 3 to the 4th is 81. And that's kind of interesting here. So see, the 3 to the 4th is equal to 81, and then 9 squared is equal to 89, or 81. Something like this. 4 to the 3rd is 64, but 8 squared is also 64. So knowing those, you have to know which one you need to use. So you have to know, am I looking at a square root or 4th root? Because that will tell you whether you're going to rewrite it as 9 squared or 3 to the 4th, for 81, for example. So I have those on the list, and here's 16 is another one where they show up in multiple lists, and so you need to know by context which one's the most useful form for you to use. And then out of the 5th powers, I would not know anything more than 2 to the 5th is 32. Because those are the most common things. Anything beyond that, I would just use your calculator, or use a different way to break it down. But these are the ones that show up often enough that I do recommend memorizing them, or at least having a list handy so you can refer back to it. So we're going to do some roots with other exponents, other you know, the root symbol there, the index, the indices. So we'll do things beyond the square root. We'll look at cubed roots, fourth roots, and fifth roots. And so these are all ones that are on that list. So the cubed root of 125. So when I see something like this and it's not like a square root, I usually will rewrite it in its exponent form. So I'll go back to that list. 125 is 5 cubed, so I'm going to rewrite it as the exponent form. And then the key here is that if you've got the same number outside as you have on the inside, those basically completely cancel out. The whole radical cancels out, that whole symbol, and you're left with just the base, what's underneath the exponent, so you just get 5. So I recommend for the higher roots to get into the habit of rewriting these things like this. So that way you can get used to the fact that these cancel out, because that's going to be a skill if you go on a college algebra that is going to come in handy. Now, the fourth root of 16. So most people say, oh, 16 is 4 squared, but then you get a problem because these don't match. The exponent on the 4 is not the same as the root that we're taking. They don't match, and they have to match in order for those to cancel out. So this is where knowing these other exponents is helpful. Knowing that instead, because I'm doing a fourth root, that I'm going to want to rewrite this as to the fourth instead. Now let's just say you didn't realize that, you didn't have that memorized, and you're like, shoot, what do I do? Well, we could do something a little tricky and rewrite 4 as 2 squared. So I just rewrote 4 as 2 squared, and then we still have that other 2 on the exponent there. If you do this, you can see that if you follow the rules of exponents, that you can multiply those exponents. And so that will give you the fourth root of 2 to the fourth when you multiply those exponents together. And you get to the same point that you would have if you had memorized this table. So if for whatever reason you didn't remember the table, you can actually get to the same point just using what you do know, that 2 squared is equal to 4, and then using our rules of exponents. And once you get to the point where you've got the same number on the exponent as the root on the outside, those cancel, and you're just left with 2. So the next one here is we've got the fifth root of 32. So if you know your chart and you memorize your chart, we're going to be looking at, 2 to the 5th equals 32. So you're going to rewrite that as 2 to the 5th. But let's say for whatever reason you didn't memorize that, you didn't have that memorized, and for whatever reason my circle won't delete, so we're just going to have some random circle there on the screen. Let's say you didn't remember that 32 was 2 to the 5th. But you do know, you can say, oh, but 32 is, let's see, that is 16 times 2. So let's say you're like, okay, I know that 16 times 2. We want to try to get at an exponent of 5 here. And so you're like, okay, I don't have anything with an exponent of 5, but let's try splitting 16 up. I know that 16 is 8 times 2, so I can split that up. So you split that up and you're like, okay, well, still not there. I've got 2 2's, so that's 2 squared, but I'm not anywhere where I need to go. And so you can keep kind of following this pattern. Or what you could do is just do the prime factorization. So that's essentially what I'm doing here, is I'm going to do the prime factorization. And let's just keep going. 8 is 4 times 2. 4 is 2 times 2. So if you don't remember, you can go back to the prime factorization. We talked about this at the very beginning in class of fractions. We talked about it when you're looking at like the greatest common factor and the common denominator. So it's popped up multiple times. It's a great skill. So what you could do is do the prime factorization and say, okay, how many 2's do I have here? 1, 2, 3, 4, 5. So the prime factorization of 32 is equal to 2 to the 5th. So you can get to that same point just by breaking it up into pieces. And then once you've recognized that, you're like, okay, I've got a 5 on the outside, a 5 on the inside. That means those cancel, and my answer is 2. Next one here, we have the cubed root of negative 27. So if there is a negative and it's an odd number in the root, the first thing I do is I know that my answer is going to be negative. And so I will just pull out that negative and then look at the cubed root of 27. So that works whenever it's an odd number that you're taking, that is the root. So this works because, oops, trying to get to my highlighter. This works because the 3 is odd. It has nothing to do with the number 27. It's because of the index that 3 is odd. So because that 3 is odd, I can pull that negative out because I'm going to get a negative result. So once I do that, then I say, okay, 27, and you want to write it as an exponent of 3. So if you go back to the list, this is equal to 3 cubed. So then you're going to rewrite that and you're going to say, okay, I've got the index, that's the same as my exponent. Those are going to cancel out the root symbol, which leaves me with a negative 3 as my final answer. So you're left with a 3 that was underneath when you ignore the exponents because it's canceled out, and then you have that negative in front. The next one we have is the 4th root of 1 over 81. So I'm going to do the same trick that I did with that other fraction, and I'm going to split this up. So we have the 4th root of 1, and then the 4th root of 81. So the 4th root of 1 is 1. It doesn't matter if it's the 5th root, the 6th root, it could be the 100th root. It's always going to be 1. And then we've got the 4th root of 81. So we want to rewrite 81, and 81 is equal to 3 to the 4th. We want to use one of the 4th powers because that's the root that we're taking. So this is 3 to the 4th. So my index will cancel out the exponent, so it cancels out that root, and we're left with 1/3 is your answer there. Then the last one, we have a negative 5th root of 1. So if that negative is outside, it's just we're going to get a negative answer here. So you can treat it as if there's parentheses around here. That negative is going to make whatever answer we get negative. So the 5th root of 1 is 1. So this is just going to give us negative 1. So I'll kind of box these to make them stand out. Are there any questions on these?
Questions here.
Okay. Now, if you were wondering, how can I do this on my calculator? Some calculators have a button, or they will have something that, for me, it's above my exponent button. And it has the square root symbol, but with an X. So it's different. So for me, so I have that above my caret button. It's kind of written over there. it's different from the actual square root, which I have above my x squared button. So the difference is that it has a little x. So that allows you to take some of these roots. And I think I'm going to test out how I use it on my calculator. It gave me syntax error, so like obviously I didn't use it the right way. There we go. So let's say I wanted to do the first one and take the cubed root of 125. I would have to type in the number 3 first to tell it what root I'm doing. Then I will make sure I have that symbol for the radical with the x up there. And then I would type in 125, and then I would hit my enter button. And that comes out to 5. So if you want to double check your answer with a calculator, most calculators have an ability to do this. It's just a matter of learning what symbols to use. And if you don't know how to use it, Google is really good. I usually just Google the name of the calculator and how to, and then I type in what I need to do, and I'll find like a manual or somebody else asking how to do it. Okay, so I've basically been doing this already, showing you how this works, but what I've been doing basically is using this rule for square roots where the root and the exponent cancel. So we've got two different rules versus whether it's an odd or an even. So when we say odd or even, when we say odd here, that means the n, the number that's up there. And then even, that's the number there. So this special rule is for the even. Technically, when you are canceling these out, you always end up with the absolute value of your answer because we can't have negatives coming out of a square root. Most of the time we assume it's always going to be the positive. It's a variable, so it doesn't matter. But just as to kind of demonstrate this, so let's say I had a square root and then I had -2 squared. So normally the square root and the square root cancel, but then you're left with a negative. But you can't have negatives coming out of a square root. It doesn't work. So our answer is really the absolute value of -2, which is equal to +2. And this would be equal to, if instead of using this rule, if you squared the -2 first to get 4, and then we take the square root of 4 and that gives 2. But most of the time you don't get situations like this often. And we usually write it in such a way that we tend to get the positive. You're not going to run into this too much and have to worry about the absolute value, but it is technically part of the definition. And whenever we have variables and we don't know if it's going to be a positive or negative coming out, we just assume that it's going to be positive. So like if you had the square root of x squared, we just say it's x. We don't bother putting the absolute value symbols around the x. We just assume it's going to be the positive one. It just makes life easier. But it's just a little note, and very, there will be few situations where you have to remember, oh wait, this is going to be the positive, I have to take the absolute value, but it doesn't happen too often. With odds, it doesn't matter. So with that said, we're going to start looking at what to do when you have variables. Now, when you have variables, it's easier actually than working with numbers. It's way easier than working with numbers because you don't have to memorize what any of these numbers are. You basically just divide your exponent. So if you're taking the square root of something, you're just dividing your exponent by 2. So if I took the square root of x to the 4th, that will give me x squared because 4 divided by 2 is 2. If I had the square root of x to the 6th, 6 divided by 2 is 3, so that will give me x to the 3rd. So when you have roots with variables and exponents, you're just dividing the exponents. It's so easy. And with the cubed root, just instead of dividing by 2, you're dividing by 3. So if you have x to the 6th, to cancel out the root, you do 6 divided by 3, that gives you 2, so your answer is x squared. And then x to the 9th, 9 divided by 3 is 3, your answer would be x to the 3rd. So the key is you need to make sure whatever your exponents are inside the roots can be divided out. You have to get whole numbers out in order for this to work. If it doesn't give you a whole number, then you just leave it inside. But if you can divide it and you got a whole number, you can just cancel it out. You don't even have to think about what number equals this. You're just literally doing division. It's wonderful. The other thing, oops, there we go. That's what I wanted. I didn't mean for that to be transitioned on another slide. I just wanted to be flat on that slide. Another rule that we're going to use in the next couple of examples is called the multiplication property of roots. And this technically isn't written about until 8.2, but it comes in handy. And it just simply means that if you have two things multiplied inside a root, you can split it up so that they're kind of multiplied separately, but they still have the same root symbol. It's the same thing that I did with those square roots of the fractions, where I split it up so that you had it on the top and the bottom. It's the same thing. You just can split it up, and it makes things easier to work with. So just a little caveat there. So we've got all these roots, and you may think, oh my goodness, these look so complicated. How the heck am I going to simplify these? But it really is simple. It's so much easier than numbers. So top left, I have the square root of z to the 20. So since it's a square root, that means you can divide your exponent by 2, and your answer will be z to the 10th. And that allows you to basically cancel out the square root symbol. For the middle, we've got the square root of t to the 50 and then s to the 60. So the first step here is I separate these out so that I have a square root symbol for each of them. And then it's the square root. So we're going to divide each of those exponents by 2. And this gives you t to the 25th, s to the 30. Most people won't do that middle step that I showed, but it's good practice to do that until you can do this in your head. The one on the right here, we've got the cubed root of x to the 33. So cubed root, you're going to divide it by 3. So you're going to take 33 divided by 3, that's 11. So our answer is x to the 11th. Now on the bottom, they get a little more complicated because they involve numbers, but it's really not so bad. So bottom left, we've got the cubed root of negative 27 x to the 27th. So I'm going to split this up so I have the number part separate from the variable part because they play by two different rules. So I have the cubed root of negative 27. So the cubed root of a negative is always going to give me a negative answer. So I'm going to pull that out. And then that gives me the cubed root of 27. And then I've got this cubed root of x to the 27. So I'm going to take the exponent 27 divided by 3, which gives us 9. So this is going to be x to the 9. Now, the cubed root of 27, we actually saw this earlier, that's equal to 3. So this is going to give me a negative 3x to the 9. So I separated out the number part from the exponent part, did the number part, did the exponent or the variable part, and then I combined those back together. In the middle here, we have the square root of 6w squared. So this is actually using the fact that Going back there. We're basically using this rule that it cancels out because we have variables, we're just assuming we don't need the absolute value part. So because the whole thing in parentheses is squared, I can cancel that out and I'm just left with 6w. Because that whole thing is squared, so that square root cancels out the square, and you're left with whatever's underneath it, which was in parentheses. Now, on the right here, I've got a negative that's outside the square root, so that's okay. And then I have square root of 36 times w to the fourth squared. So I'm going to separate out the number. So we've got 36, and then I've got w to the fourth squared. So square root of 36 is 6. 6 squared is 36. So this is going to be negative 6. And then that square root and the square cancel, and you're just left with w to the fourth. And that's your answer. Are there any questions?
Yes.
Okay.
I think I'm answering it in my head as I'm thinking of it.
That's fine.
So on the last question with the w to the fourth power squared, as long as they're both even, it can cancel the outer one out?
The outer one is canceled out because it's a square root.
Okay, because it's a square. Okay.
Yeah. So if you want to write that 2 out there to kind of help you, you can do that.
Okay.
Yeah.
That makes sense. So and then it would go like if it's a cubed square root, principal square root, and then if there was like the same thing, a W4 but with a 3, then that would cancel out.
Cancel. Yes.
Okay.
Yeah.
Thank you for clarifying that.
Yep. Yeah. So if this was a cubed root and then this was a 3, those would cancel. You're still left with w to the fourth.
Okay. Thank you.
Yeah. You're welcome. Now another thing is some people, instead of just doing w to the fourth and then taking the square root, some people see that and they're like, oh, I want to multiply those exponents. So you would do 4 times 2, which is 8. Now you're just taking the square root of w to the 8, which is that rule where you're dividing the exponent by 2. So you still get w to the fourth if you were to do it that way instead. If instead of seeing, oh, the 2's cancel, if instead you multiply them and then try to cancel it. So you get the same answer, depending on how you want to look at it, basically, whatever works for your brain. Do you have any other questions?
No, that's all for right now.
Okay, well, that's all I've got for this section.
Wow, nice.
A lot of people get freaked out about this stuff, and it's like, it actually is not so bad. It's not so bad. I find it kind of fun, but, I like math.
And now that I'm getting used to it, it's getting better, but at first it was kind of hard. But I just kind of slept on it a couple nights, and it helped. So it's a little different.
Yeah, and the one thing that I've noticed about math is that oftentimes it ends up being easier when you work with variables than if you're trying to do stuff with numbers. Like, I'm like,
yeah, I've seen that.
When we're factoring out greatest common factors, it's so much easier to factor out just a variable than to factor a number. And it's like, wow, why can't we just have letters everywhere? I don't have to think as much.
Right.
So. All right.
Thank you so much.
Thank you for attending, maybe being able to come with the change in date.